The periodic table includes a place for all the elements that have been discovered. Metals are found on the left, and nonmetals on the right. Elements with similar properties are grouped together in columns, but the elements haven't always been arranged in this way. It was in 1869 that the brilliant Russian scientist Dmitry Mendeleev worked out the basis of the modern periodic table. He was a fanatical card player. His favourite game was patience. By Mendeleev's time, 63 elements had been discovered, but scientists couldn't agree on how to arrange them in a useful way. Mendeleev wrote each element's symbol on a card, along with a value called atomic weight. He was determined to find a pattern which would link groups of similar elements. One group was the reactive non-metals: fluorine, chlorine, bromine and iodine. Another group was the reactive metals: sodium, potassium, rubidium and cesium. Mendeleev was convinced that an overall pattern existed. He tried arranging the cards in different ways. But after 3 days and 3 nights, he still hadn't found a solution. Exhausted, he fell asleep. Miraculously, as he dreamt, he began to see the pattern he'd been looking for. Mendeleev's answer was to arrange the elements in columns in order of atomic weight. By doing this, groups of similar elements could be grouped in the same row, like the alkali metals and the halogens. The properties of the elements repeated in a series of periodic arrangements, so he called it the periodic table. Mendeleev was so convinced his pattern was correct that he left spaces. This was his stroke of genius. He reasoned that there were still more elements to be discovered that would fill these gaps. He even predicted the properties of these unknown elements based on their position in his table. If the table really could be used to predict the existence of elements, then other scientists would have to agree that Mendeleev's ideas were right. 6 years later, a new element called gallium was discovered. Its atomic weight was almost exactly the same as Mendeleev's prediction. This happened again with 2 other elements filling gaps. From then on, Mendeleev's table was accepted by scientists. Today, the layout of the periodic table looks slightly different. While Mendeleev wrote his original table in columns, the modern table is arranged in rows. Over 60 elements were known to Mendeleev. Today, we know of more than 100. Each with its own place in the periodic table. And nowadays, elements are written in order of increasing atomic number, not atomic weight. The position of any element in this table allows its properties to be predicted. The noble gases are found in group 0 of the periodic table. There are 6 elements in this group: helium, neon, argon, krypton, xenon and radon. Their position in the table means they have a common electronic structure. Helium has a full outer shell of electrons, as does neon. Going down the group, there's always a stable outer shell of electrons. This makes the noble gases very stable and unreactive, which also makes them extremely useful. Perhaps the most familiar use of the noble gases is in glowing neon signs. These are lamps usually constructed from clear, colourless glass tubes. The tubes are filled with neon or argon, or a mixture of both gases. To start making a neon sign, the glass tube is very skillfully bent into the right shape. Next, an electrode is fitted to each end of the glass tube. Finally, the noble gas is introduced at very low pressure and the tube is then sealed. When an electric current is passed through the gas, light is emitted. Even at high current, the gases don't react, so these tubes can last for up to 30 years. Pure neon produces orange-red light. Argon produces a blue-green light. Helium produces a pale pink light. A whole array of other colours can be produced by using tubes with fluorescent coatings. Argon is used in fluorescent tubes for sunbeds. Under the right conditions, an electric current passing through this gas produces ultraviolet radiation. Because argon is a very unreactive gas, it's also used in welding. The hot welding metal is surrounded by a flow of invisible argon. It prevents the metal from reacting with oxygen in the air. Deep-sea diving is one of the more surprising applications of a noble gas. Helium is sometimes used in breathing apparatus. Pure oxygen can be toxic to the human body, so it has to be mixed with other gases. The air we normally breathe is mostly a mixture of oxygen and nitrogen, but some deep-sea divers use a mixture that also contains helium. This allows them to dive to greater depth for longer periods of time. So far, we've looked at the chemical properties of the noble gases, but their physical properties also make them useful. Take density. This airship can float through the sky because it's filled with helium gas. Helium's less dense than air, so the airship rises upwards. To compare the densities of the noble gases, we're going to use balloons. We know helium is less dense than air. No surprises, the helium-filled balloon rises. This balloon is filled with neon. It slowly sinks to the ground. Neon is more dense than helium. What do you predict will happen to other balloons filled with argon, krypton and xenon? Xenon sinks the fastest. Krypton takes a bit longer, followed by argon. The noble gases become more dense as you go down the group. The large block in the middle of the periodic table is home to the transition metals, including well-known metals such as iron, copper, gold, and mercury. Other more unusual transition metals include scandium, niobium, and ruthenium. They all have similar physical and chemical properties. Transition metals are much less reactive than the metals in Groups I and II, so in general the transition metals are more useful. But all metals have the following physical properties in common. Metals are hard. Many tools are made from metals because of their hardness. Metals are shiny, so they're widely used to make decorative items. Metals are malleable. They can be hammered and bent into different shapes, resulting in these fine items of jewellery. Or this huge modern sculpture. Metals are ductile. They can be drawn into wires, again making them useful in jewellery and construction. Metals are strong. The metals in these bridges have good tensile strength for supporting heavy loads. Metals conduct heat. Thermal images of a saucepan on a hot plate show that heat energy is easily conducted through the metal pan. Metals also conduct electricity. Place any metal in a circuit and it'll allow electricity to flow. Most metals have high melting and boiling points. A tungsten filament has a melting point of over 3,000 degrees Celsius. Metals are also sonorous. This means they produce a sound when struck. Alloys containing the transition metals copper, nickel and zinc are used in coin production. A mixture of metals is used because it's stronger and harder than pure metal. What other properties make metals suitable for minting coins? Some transition metals can be used as catalysts to speed up chemical reactions. The transition metals platinum and rhodium are the catalysts in catalytic converters. These speed up the chemical reaction between carbon monoxide and nitrogen monoxide produced in engines. These polluting gases combine to make carbon dioxide and nitrogen. This is how a catalytic converter reduces the emission of pollutants. The solutions of transition metal compounds are often very colourful. Because of their bright colours, transition metal compounds are used to produce the vivid colours in pottery glazes. They add colour to the surface of the clay. To show the range of glazes, this potter is making some test samples. First, the fresh clay is moulded into shape. It's then fired to dry it out and prepare it for glazing. Next, the clay shapes can be dipped into glaze mixtures. These contain different transition metal compounds. The glaze coats the surface of the clay. Finally, the shapes are placed in a kiln for a second time and heated to a very high temperature. The result is an array of different colours, provided by the compounds of different transition metals. And different compounds produce different colours, depending on the type of clay that's used. How to arrange them in a useful way. Mendeleev wrote each element's symbol on a card, along with a value called atomic weight. He was determined to find a pattern which would link groups of similar elements. One group was the reactive non-metals, fluorine, chlorine. It was in 1869 that the brilliant Russian scientist Dmitry Mendeleev worked out the basis of the modern periodic table. He was a fanatical card player. His favourite game was patience. By Mendeleev's time, 63 elements had been discovered, but scientists couldn't agree on periodic table includes a place for all the elements that have been discovered. Metals are found on the left, and nonmetals on the right. Elements with similar properties are grouped together in columns. But the elements haven't always been arranged in this way. Bromine and iodine. Another group was the reactive metals: sodium, potassium, rubidium and cesium. Mendeleev was convinced that an overall pattern existed. He tried arranging the cards in different ways,